Alright, everyone. I promised that I would make a reaction coordinate diagrams video. I'm sorry this came a little late. Ran into some technical issues, but now that I've got that out of the way, I hope this still comes in handy and useful for you guys as you prepare for the exam on Monday, which is tomorrow actually. So I'm just gonna go ahead and cut out all the hodgepodge of information that you don't need. Rather, you're gonna get a question in the midterm that looks something like this, where they give you reaction conditions and you need to be able to process these information to give the right answer. But before I go into an example, I just want to give you some summary tips. Yeah, for lack of a better term, I guess. But alright, all you need to know is that for all endergonic reactions, they're the same thing as endothermic. They have, hang on, just give me 1 second. They have a positive delta G. Okay, and which means that exergonic reactions are also known as exothermic, have a negative delta G. And what it means is that for a reaction to proceed, which if you're going to take physical chemistry, you're going to learn that a lot. For a reaction to proceed spontaneously, delta G has to be negative. Which means that the reaction goes forward. If delta G was positive, it's known as a non-spontaneous reaction. Where it's going to go backwards. And what do these arrows kind of tell you? Hopefully right off the bat you can understand that a negative delta G is going to favor a product formation, and a backwards arrow is going to favor a reactance direction. So that being said, whenever you get something known as an endergonic reaction or an endergonic overall reaction, you know that the way you draw your coordinate diagrams have to favor your reactants. Okay, let's talk a little bit about K values as well. You might see some stuff like K equilibrium from your general chemistry, and all you gotta know is that when it's less than 1, the reaction is non-spontaneous. Okay, when it's equal to 0, there is the system's equilibrium. And when K at the equilibrium is greater than 1, that's when the reaction becomes spontaneous. So I'm gonna just highlight the delta G negative ones that you need to know. So when you have a negative delta G, your reaction is gonna be exergonic, your reaction is gonna be spontaneous, and your K equilibrium is gonna be greater than 1. So that should be big signs that you should be able to process, and vice versa. When you get a positive delta G, you're gonna have an endergonic reaction. Your reaction is going to be non-spontaneous, and your reaction is going to be having a K value of greater than 1. Okay, let's go ahead and do an example. Hopefully that will help you understand the concept a little bit better. Alright, so given the practice midterm that you have on Blackboard, you should see the same thing. It's question 5, I believe. Let me see. It's question 6 on the practice midterm. So you got a question that says that the intermediate process is anorganic and is also the slowest step. And overall starting material to the product is going to be exergonic. Now, when you see the word slowest step, it's analogous to the term rate determining step. They mean the same thing. Okay, now let's break it down into little pieces. I'm just going to use the pink marker for the first part, where we say that the transition from starting material to intermediate is going to be endergonic. What does that tell you then? Delta G is positive. Delta G positive. Okay, and it's also going to be the slowest step, so your activation energy is going to be high. Alright, now, so arbitrarily, I'm just going to draw my starting material, and right here, I'm going to stop here where my intermediate has a positive delta G, and it's also going to be the highest EA. Now, we can move on to, so what I'm doing right now is just drawing the skeleton of the overall diagram, and then I'm going to go explain it in detail in a bit. Okay, now from the intermediate to the product, we see that the overall starting material to product process is going to be exergonic. So delta G has to be negative at the end, which means that my products have to be at a point that's lower than my reactants, than my starting material. So my products can be somewhere here, can be somewhere here, can be somewhere here, but never at the same or above. So these places are going to be wrong. Alright, so let me just go ahead and draw something like that to denote the second part of the reaction, but that's not really it's not a really good kind of graph to draw. I would prefer if you actually showed a little bit more showed your graph a little bit more dramatically, such that the second step is lower than the first step. Okay, and then this is right here. This point right here is going to be your products. Okay, so let's go and check our work right now. You should know by now that this area right here is going to be the activation energy for the first part, and then this graph right here, this area right here rather, is going to be the activation energy for the second part. So you can just go ahead and write EA1 is greater than EA2. Was that what's required of the question? Because it said that the first part is the slowest step. So there you go, it's correct. Now, check if your products are lower than your starting materials, right? Because when products are lower than starting materials, it means that delta G overall is going to be negative. Formation of products are favored. And is that the case? Yes, you also got that right. Okay, all it's left to do right now is just to label your transition states, which are always going to be the top part of the graphs. So right here is going to be transition state 1, and right here is going to be transition state 2. Okay, and with that, you are going to get full credit for this question on the exam. Now, let's try another example where you're given, instead of the written descriptions of how the reactions proceed, you are given stuff like that, where you're given K equilibrium values, and you got to determine which is going to be your rate determining step. and how the reaction is going to proceed. Okay, now remember when we say that a K value of less than 1 is non-spontaneous, it means that right here delta G has to be positive. Okay, and then when it's greater than 1, it means that delta G is negative. So where do you think the reaction is going to go for? It's going to favor which part? Go ahead and think about it. But if you are on the same page as I am, you should know that the reaction is going to favor the products, right? Products favor. So it's going to be right here. What you're going to do is from A to B, we know that it's going to be delta G positive. So this is A, this is B. We have a positive delta G, which I'm going to use a green color to denote right here, positive delta G. And from B to C, we have a negative delta G. So from here to here, oops, sorry. B to C. So B to C right here, I'm going to use the blue one right here, B to C, negative delta G. Okay, let's see. Yeah, so what's left now is just labeling your transition states. Okay, and your activation energy. So this is EA1, this is EA2, which kind of looks a little bit different from the other graph that we drew just now, but this is the general idea, where the reactants for a positive value are lower than the products, and then the products are higher than the reactants for a K value of less than 1. So hopefully this helps. Feel free to let me know if there's any questions, and email me or come to my office hours. Good luck studying, and I hope to see you in the next video.